Hello friends, how are you? I hope you all are well. Today the concept is continuous charge distribution. It is a small concept of electrostatics, but it is important, no doubt at all. So I hope that you might have subscribed my channel. If you have not done, do it as early as possible. As a result, you can get the information immediately which can help you to continue your study. I hope that you will watch the video from first to end. So today's topic is continuous charge distribution. In fact, we know that charge is discrete. We can't think a charge less than basic charge. Less than basic charge in the sense that either the charge of electron or charge of a proton, because we know that charge can be quantized. We find the charge in an integral multiple. All the time we find the charge in an integral multiple of basic charge. Basic charge means the charge of an electron, or you can say charge of a proton. So in a extremely closed space, in an extremely closed space, charge forms continuous charge distribution. It is customary to define the charge distribution in terms of density. That means here we will discuss about the different types of charge distribution in terms of density. So there are three different ways of charge distribution is there. One is the linear charge density. Linear charge density. Second one is the superficial charge density, means it is related with the area. This is related with the length. Third one is the volumetric charge density. Linear charge density denoted by the letter lambda. Superficial charge density denoted by the letter sigma. And volumetric charge density generally represented by the letter rho. So at first I shall explain what is linear charge density. See here, for example, we have taken one conductor. In this conductor, we supplied the charge Q. The charge Q is distributed uniformly. Here charge density means the charge present in unit length. We have taken one conductor whose diameter is negligible in comparison with its other dimensions. So, whenever I am telling about the linear charge density, that means the charge present in a unit length. Suppose this is the unit length, charge present in unit length. Suppose the charge is Q, the length is L, then lambda is equal to Q upon L. The ratio between charge to the unit length. I have taken unit length, but one problem is there. For example, we have supplied the charge. The charge is distributed like this. See, that means here the charge is not distributed uniformly. In this case, the charge is distributed uniformly. I have taken charge to the length, unit length. Small charge I have taken, small length. Okay. But in this case, I said that suppose the charge is not distributed uniformly. Then what about the charge here? What about the charge here? What about the charge here? So in this case, we have to consider a point charge. That means the charge present in a small point. So I can say that this lambda, mathematically this lambda is equal to dq upon dl. Here dl is the, I have taken very small length. The charge dq is a very small charge. So we can calculate the linear charge density at a point is lambda equal to dq by dl. I can write like this way, dq is equal to lambda into dl, or I can say that this charge I am taking the integration lambda dl. Here integration over the length, because this is linear charge density. So the charge per unit length, charge per unit length. So this is about the linear charge density. Next one is the superficial charge density. What is this superficial charge density? Superficial charge density. The sigma is the symbol. Let us see, for example, this is some surface area. You think that this area is 10 meter square, 10 square meter, and we supplied the charge of 20 coulomb. Then what about its density, charge density of area? Superficial charge density, or I can say that charge density of area. Here how much charge present in unit area? We have to calculate from for unit area. Suppose 10 meter square, this is the surface. Here the charge is 20 coulomb. That means 1 meter square surface, the charge is 20 upon 10. That means this is 2 coulomb per square meter. Coulomb per square meter is the SI unit of charge density of area, or we say superficial charge density. So, suppose the charge is not distributed uniformly. If it is distributed uniformly, I can say that sigma is equal to dq upon dA. Here A is the surface area. So this is the charge density at a point. Charge density at a point. I can write this one as dq is equal to sigma into dA, or I can write that if I take the integration, it will be sigma dA. So this is the integration over the area. So I have to calculate the charge present in unit area. So its SI unit will be, this is charge is the coulomb, area is the coulomb per square meter. This is about the superficial charge density or charge density of a area. Next one, volumetric charge density. Volumetric charge density, okay, or you can say charge density of volume. It is denoted by the letter rho. Suppose this is Q-shaped object, okay. So here we are considering a small volume. We are considering a small volume. So the charge is also very small. So I can write that this rho is equal to dq upon dv. The density at a small particular point. Mathematically, it is a ratio between charge to the volume. So far as its unit is concerned, I can say that the charge is coulomb, volume is cubic meter. Okay, so now I can say that this dq is equal to rho into dv, implies that q is equal to rho into dv. This integration over the volume. So this is about the continuous charge distribution. I said that when extremely large charges are present, we feel these are distributed just like number of cars are standing on the road. You are observing from certain height. It seems that all these cars are in one line. It is an example of a linear charge distribution. So I hope that you might have understood the continuous charge distribution what I explained in terms of density of a charge. So that's all for this video. Until the next video, bye.